You slide into a white tunnel, and the machine starts making noise. Loud, rhythmic, almost industrial. You are not moving. Nothing is touching you. No dye has been injected, no radiation fired through your body, and yet within minutes, a doctor will be looking at a three-dimensional image of your brain, your spine, or your knee in more detail than any X-ray could ever produce. No cutting, no contact, just magnetism and radio waves. The real explanation for how that is possible is one of the strangest things physics has ever handed to medicine. Everything starts with a fact about your body that you never think about. You're made mostly of water, and water is made of hydrogen atoms, and hydrogen atoms have a nucleus, a single proton, that behaves like a tiny spinning magnet. Under normal conditions, all those protons spin in random directions, canceling each other out. They are chaotic, unaligned. But when you slide into an MRI machine, something changes. The machine generates a magnetic field roughly 60,000 times stronger than the Earth's own. In that field, your protons stop being chaotic. They align like compass needles all snapping to face north at once. This alignment is the foundation, but it is not the image. To create an image, the machine then fires a pulse of radio waves at a very specific frequency, a frequency tuned exactly to the resonant frequency of hydrogen protons in that magnetic field. This is called the Larmor frequency, and it works the same way a tuning fork works. Strike the right frequency, and the protons absorb the energy and tip out of alignment. Stop the pulse, and they snap back. As they snap back, they release that absorbed energy as a radio signal. That signal is what the machine detects. Here's where it becomes remarkable. Different tissues in your body contain different concentrations of hydrogen. Fat, muscle, fluid, bone marrow. Each releases a slightly different signal as the protons relax back into alignment. The machine measures two specific relaxation timings. T1, which tracks how quickly protons realign with the magnetic field, and that's it, T2, which tracks how quickly the protons lose synchrony with each other. By recording these timings in thousands of tiny locations across your body simultaneously, the machine builds a map. Brightness in the final image corresponds to signal strength. Dark areas correspond to tissues that return little signal. The contrast you see between a tumor and healthy tissue, between a torn ligament and an intact one, comes entirely from these differences in how hydrogen atoms behave in different biological environments. The spatial precision comes from a technique developed by physicist Paul Lauterbur, who won the Nobel Prize in 2003 alongside Peter Mansfield for their foundational work on MRI. Lauterbur realized that by adding smaller gradient magnetic fields on top of the main field, fields that vary slightly in strength across different locations, you could give every point in the body a unique magnetic signature. Protons at different locations resonate at slightly different frequencies because the field strength is slightly different where they sit. The machine uses this to know exactly where in the body each signal is coming from and assembles the full image slice by slice. The loud knocking you hear inside the machine is the gradient coils, large electromagnets that switch on and off rapidly to create those location-specific field variations. Each bang is a coil activating. The faster and more precisely they switch, the higher the resolution of the final image. Modern machines can resolve structures less than a millimeter across, fine enough to see individual layers of the retina, fine enough to detect a lesion smaller than a grain of rice. The superconducting magnet that generates the main field runs at minus 269 degrees Celsius, close to absolute zero, cooled by liquid helium. At that temperature, the electrical resistance of the magnet's coils drops to zero, allowing enormous currents to flow without generating heat or energy loss. This is what produces a field powerful enough to do everything described above, and it runs continuously 24 hours a day for the entire working life of the machine. Because switching it off and restarting it costs hundreds of thousands of dollars and weeks of downtime. So the next time you slide into that white tunnel and the machine begins its loud, rhythmic knocking, you are not being scanned. You are being listened to. Billions of hydrogen atoms in your body are absorbing energy, tipping, snapping back, and broadcasting a signal. And the machine is translating that signal with extraordinary precision into a picture of you.